All right. Hey, everyone. So I'm just going to explain 2.5.3 TST, the teacher scored test. I'm going to give you some hints on where to find some of the stuff, and I'm also omitting some of the questions. So for question 1A, part 1 is 2.1.1, page 3, and part 2 is also on 2.1.1, page 3. And then the third part, they didn't really address this in the text. I think what they're getting at, you can just write this as your answer. The rates of the reaction at equilibrium, once a reaction has reached equilibrium, the forward reaction and the reverse reaction the rates are equal. Okay. The amounts of reactants and products are not always equal, but the rate of the forward reaction and the rate of the reverse reaction are equal, which means the amount of reactants and products are no longer changing. So the way that the book explained it, I didn't really like. Think of it this way. Imagine I have 25 kids in my classroom and they're the reactants, okay? And then there's an empty classroom across the hall. That's the products. So I start out with all reactants and no products. And let's say I tell my class, okay, you can choose which room you want to go to. In my room, we're going to have a silent reading of the chemistry textbook, and across the hall, there's going to be a pizza party, okay? All of the reactants, all the students, would immediately get up and go across the hall and probably stay over there for the pizza party because that's more favorable. That's more fun, okay? That's an example of a reaction that goes to completion. All the reactants completely turned into all products, okay? That's a reaction that goes to completion. A lot of reactions, though, are reversible, okay? Or they don't go to completion, where the products are not necessarily way more favorable than the reactants. So let's say we start again with all 25 kids in my room. And then and I tell my students, okay, you can either stay in here or you can go across the hall. In here, we're going to play board games. And across the hall, there's going to be a movie, okay? And so immediately what would happen is some students would get up and leave my room. So the rate of that reaction of people leaving my room would be very quick, okay, at first. But then once everyone kind of settled down into their more favorable location, the movement would kind of calm down. And if it was a really good movie, maybe 20 students would be across the hall watching the movie, and 5 students would have stayed with me playing board games, okay? And they could still be free to go, but I would say that that ratio is kind of where things would settle down. So people would still be moving back and forth. Maybe they'd get bored with the movie and come to the game. Maybe someone would get bored with the games and go to the movie. But eventually things would calm down and you would kind of have a point where the concentrations of students stop changing, okay? There were always 20 kids across the hall and 5 kids in my room. And the forward and reverse reactions were still happening, okay? But that we got to a point where those were happening at the same rate. Rather than everyone going across the hall like they did at first, we reached equilibrium, okay? Where the amounts of students stopped changing, even though there was still kind of an occasional back and forth between the two rooms. And that's how equilibrium works, okay? You start out with all reactants. At first, a bunch of reactants convert to products. But then depending on which is more favorable, the reactants or products, the system reaches equilibrium, where the concentration of reactants and the concentration of products stop changing. They're not equal, okay? Depending on which one's more favorable, the concentrations of reactants might be really high and products is low, or vice versa. But you get to a point where the concentration stop changing and the equilibrium mixture has a fixed concentration of reactants and products, okay? So I think that's a better explanation of equilibrium than what the textbook did. The equilibrium constant expression is when you take the equation or the chemical reaction and you turn it into, I gotta focus this a little bit better. Good. And what they've experimentally determined is that at equilibrium at a given temperature, the ratio of the reactants, the products to the reactants is always the same, okay, if the system is at equilibrium. So what they do is they took this equation, turned it into the equilibrium constant expression that looks like that. And it's saying if a sample at equilibrium contained 0.051 molar H2, 0.087 molar S2, and 0.97 molar H2S, what would be KEQ? So all you need to do is plug this in for H2S, and you need to square it because that's squared. Plug this in for H2 and square it. and multiply that by S2, which is, this one is not going to be squared, okay? And then type all that into your calculator, and that'll give you the value of KEQ, okay? And then part 2 is on 2.1.1, page 18 to 20, okay? And then part C, once again, they gave you the equation and the equilibrium constant expression. And they're asking what would be the equilibrium concentration of NO. So they're asking you to solve for NO, okay, the concentration of NO in a gas mixture that contains 1.7 molar SO3. So NO is our unknown, so I'm going to call that X. SO3 is 0.070. Okay, the concentration of SO2, oh no, sorry, SO3 is 1.7. And then the SO2 is 0.070. And then the NO2 concentration is 1.3. Okay, so for this one, none of them are squared. Okay, and then that's saying that KEQ, this value is going to be 10.8. Okay, so what they want you to do is solve for the unknown. Okay, so the way I would solve this is I would do 10.8 equals X times 1.7, and then I would simplify the denominator, 0.070 times 1.3, and you get 0.091. Okay, and then to solve for X, I would multiply both sides by 0.091. Okay, so 10.8 times 0.091 is 0.9828. And then on this side, because these are going to cancel out because they're in the numerator and the denominator, equals X times 1.7. And I'll leave the rest to you to solve for X. Okay. All right, question 2. This is the acid-base reaction. It's asking for the areneous acid and the areneous base. That you can find that in 2.1.3, page 2 to 4. It's asking for the acid and the base from this equation. Okay, this chemical equation right here. This part 2 is actually in a totally different section. That's in 2.2.3, page 3. And the type of reaction, this was not very clearly described in the textbook. The type of reaction is a neutralization reaction. When you react an acid with a base, they neutralize each other. Part B, you can omit that. That was not clearly described in the textbook. And part C is in 2.1.3, page 17. The next part, question A, what is the pH of this solution? Okay, so the formula for pH is on in 2.2.1, page 14. Actually, I'll just tell you the formula right now. It's because I want to show you a couple things. pH equals negative log of the concentration of H+. Okay, so to find the pH of this, you would do the negative symbol, press the log button, okay, which is right here, and then it opens the parentheses for you, and you can do 6.3 times 10 to the negative 10th, and you can close the parentheses like that. Okay, so that's how you would find the pH. And then for pOH, the formula is a lot more simple. You can look at 2.1.1, page 17. You're going to use your answer to A to answer part B. Okay. And then on this next page, okay, they give you the K for this. Essentially what this is this is HF breaking apart into H plus and F minus. So they turned that into an equilibrium constant expression. So they're telling you the concentration of H plus and F minus are that. So you're going to plug this number in here. You're going to plug the same number in there. Okay. And then you're going to divide it by this number. And you're going to multiply them by each other because they're next to each other. And then you're going to divide it by this number, and that will give you the value for Ka. And then for part B, do 2.2.3, page 17. Question 5a, you can omit that. I don't think that was really in the book. For part B, you're going to use this formula to figure out the rate, figure out the reaction rate. Okay, the rate constant is 1 times 10 to the negative 3, and the units are kind of complicated, liters per moles per second. Rate constant is K. Okay, so the lowercase k So you plug this number in for lowercase k. And then a is going to be 3. So you're going to do 3 squared, and you'll multiply that by this value for k, and that will tell you the rate. Okay. And then part C, number 1, you can omit that. Number 2 is on 2.3.1, page 9. You actually don't really need this scenario in order to answer part 2. Part 3, I want you to omit. And then part 4, you don't just explain your answer. You don't have to draw it on the energy diagram because I know that's difficult on the computer. So just explain it in words. The answer is found in 2.3.1, page 13. Excuse me. All right, so hopefully that is helpful. That is 2.5.3, second semester 2.5.3 teacher scored unit test.